Excuse me. Okie doke. We continue in a sec. Oh, I forgot I didn't upload that part. Well, let me get my laptop real quick. Fuck it. Forgot I need to upload this because I was recording the first part of the quiz review section of chapter 8. Okie dokie. Alright, why is it fucking so sensitive to the voice? I guess it's fine now? Okay, yeah, we're good. Alright. Let me get this really quick. Oh, fuck my shoulder up. Don't know how. Almost done. Just logging into internet and then uploading. Okay. And uploaded. Okie doke. What was I about to do? I was about to do something. Oh. Okay. And we'll continue from where I left off. We were at go-to statements where we had statement labels, which is just a word followed by a semicolon without anything crazy going on. And then you can just go to that. So like if we had, just because I haven't touched these in a while, we could have, and you're doing just like case statements. So if you did switch whatever on X, and then you'd have case 1 like that. So your indentation, at least style wise, is like here. So we'd say start point. Let me name it like a namespace where it's Pascal case, I think is what it's called, as opposed to hump case or something, or camel case. There it is. So do start point, and we can build just a test. Let me move my phone. Okay. And we'll just get input and output. Need output to test go to execution flow. Okie doke. So we'll have this start point, and then we can have, we'll just output I have started, and then we'll just say go to start point. Start point. Maybe not. Maybe that's not go to. Go to. I think, isn't it? I thought it was. No, it's fine. It just doesn't. Where's the unreachable code? Line 10. Oh, because it goes and then it infinitely loops. Okay. So we'll just say we need a condition so it doesn't happen every time, and then we'll just say int x, and x is 1. Okay, and then we'll say if x is 1, we'll do this. Is it cool now? It's a condition. Even though technically it should be an infinite loop. Yes, it is an infinite loop, but it sees a condition, so it's not gonna see it. It's not gonna like this. It doesn't like it. Actually, really, that's the only reason? No, because if I killed X here, then it's not happy because unreachable code. But then if we do this, I think it would say unreachable code anyway. I think. No, it's only showing this. Okay, weird. Well, I put it as a condition here, and then if I wanted to make it not an infinite loop, then we could just say, we'll just decrement X real quick, and then why is it unreachable code? X is 1. If it's 1, we'll go to start point. Okay. And oh, wait, but I'm pretty sure we only initialize it once. So we could say maybe this is why. No. Okay, because it's only initialized once, yo. If it's 1, then we go. Oh wait, whoops, sorry. I think maybe it knows now. So this time we'll decrement x, and then now it knows it's not. Okay, well it shouldn't be. So the point is we're saying we're going here. Is it because we're reinitializing this? It seems like it has to be. So if we do this, we say, okay, I have started. X is now 1, and then we decrement x, and then we go to the start point, but then we go, and then x is now, okay, so it is reinitializing x. Okie doke, noted. Hence the spaghetti code. Alright, fuck go-tos. Okay. Yeah, because there's no clear flow. It's not this, then this, then this, and this, and this. It's this, and this. You may as well have a loop instead of just saying go to. Or like do something while something is true, and then you adjust it and then go back. That way it's clear that you're going back some set number of times that you can evaluate. Takes less effort. While loops, cool. Infinite loops, yep. The loop variables, those are like counters that tell the for loop or whatever loop how many times to loop through. So like we could say, just do this. Output to test loop count. So we could say int x, and let's say x is 5, and then we'll say while x is greater than 1, well, yeah, while x is greater than 1, what we're going to do is we're going to say x is greater than 1, and then we'll decrement x, and then boom, and then it happens a few times, and then boom. Oh, and we should be outputting what we could do right here. Boom. So it's 5, then it's 4, then it's 3, then it's 2, then it's 1. Or sorry, so it's, we're saying, okay, so we're saying it's 5, it's 4, it's 3, it's 2, 4 prints, but then it's 1, and we don't print again. Cool. So we could do that, or we could do the same thing in a for loop. X in this case would be this guy. And the problem with the while loop is because that variable has to exist before, versus if we instead just said for current loop, or yeah, whatever, current loop, and we start at 1, and then we go to total loops, and we say there are 5 loops, and we continue through this, so we have it 5 times, and then we increment, then we just do whatever here. But the point is that the current loop variable only exists in the for loop, versus a while loop, we have to define the while loop before. We can't say while something and then create that something. We could declare it and then do something, but we would actually, no, we would need to initialize it, because we can't make a comparison about its value if we don't know what it was initialized to be. So we could say it's 0, and then if that passes the test, then change it and then keep going. So like maybe we say it's 0, and then we say while it's less than or equal to 10 or less than 10, increment it and do something, and then it would happen 10 times, because 0 and then through 9, so 10. Cool. Yeah, head dangling else, go to while loops, do while loops. So we say do something and then while, and then it'll do it again. So we say do and then logic, and then at the end of it, while something. So we could say, what would be a case where we'd want to do while? We could say, oh, like starting a clock. We could say do tick sound when we start the clock. So we could say, ow, fuck, that hurts. Okay. So we could say there's some sort of function, something that calls this logic, and it is do, and it is tick sound, and then the clock makes tick sound, while clock has batteries. Boom. Is that really the syntax we're going to do it? We're just going to do... We'll just say void tick sound, tick. Yeah. Cool. And then we'll say bool clock has batteries. And we'll just say true, sure. Clock has batteries. And then after, we'll say, it'd be kind of annoying here, but it's fine. We'll say int tick count. Hasn't ticked yet, so we'll say tick sound, and then we will do plus tick count, and then we can say, all right, but then it won't, it'll expect the while clock has batteries, like that. Okay, so that's how we do it. So we leave it at the same little statement there. Boom. Okay, so it finishes like that. All right, cool. It has batteries, so here it would keep on going forever. But we could say while clock has batteries, and then we could say, and then each time we say if tick count is greater than 100, then at that point, clock has battery. What the fuck is it doing? Clock has batteries is now false. Okay. And then we could say we could have another variable, const expression, and then whatever, so that we know what the 100 actually means. I mean, we could do that right now. We could say const expression int ticks per battery, ticks per clock battery. Then we say 100, and then we could just say here ticks per clock battery. If it is greater than or equal to that, cool. Okie doke. So we say, oh, it happened 100 times. Looks about right. I was scrolling up, you couldn't really see. So clock will make the tick sound, or clock ticks. Excuse me. Batteries run out after 100 ticks. Boop, boop, like that. Cool, we'll do while. So we'd start the clock and then it would tick the first time. Instead of starting it and then, I mean, we could call the function, then it's a while, but I want to make sure that something actually starts in the beginning. That it happens once. Like if I click my mouse and that initiates eating, and then we say, hey, while still eating, finish eating or some shit. If we don't start the eating process, then I'm not eating, so I don't do anything. So we have to start the eating. Something like that. Not a great example, but because then when would it end? Well, you could have like a progress counter. So like after every eat animation, like after every little sound in Minecraft, whatever, you add 10 to the percentage or something. And then once it's 100, then you stop. You want to at least start eating. You don't just say while eating, because you haven't started eating yet. And then you could start it and then do the while loop, but it makes sense to just do and then continue it so that it happens at least once instead of having it before. And then it's everything in there is limited to that scope too if you wanted. So if you wanted to create a variable or something, you could. Okay. Yeah, the halt, so we have standard exit and then standard at exit, and at standard at exit we pass it a identifier for function. And then when standard exit is called, which it seems that we need C standard library, then we can do that. So we could say like that, and then we could also say, and we need let's just output for functions to test flow, execute, flow, and execution. And then need standard at exit, or I think it's at exit. I don't know, we'll find out. At exit would be the name, and standard exit. Cool. Okay, so we could have some function action going on. We'll just say print shit if not defined, print shit, define print shit, and then we'll just say namespace exit stuff, and things that we want to have at the end would be we'll just say fuck it, void print shit. This is actually, we need input and output here, output for print shit, so we don't actually need this here. And then this is a for declaration, so we need to implement it now. This will be called print shit, and we'll include again print shit, and then namespace, what do we call it, at exit stuff, whatever, I'll just copy her over, it's fine, like that. And then this is not a for declaration, but we've included it, so we're cool. To resolve any linker level type discrepancies, return type discrepancies, or return type discrepancies at the compilation level instead of the linker level, so it happens earlier and stops instead of compiling all the way, and then we get the issue, because compiling probably takes a while maybe. So we'll do print shit, and we'll just say clean up. Cool. Okie dokus. We'll do that. And then we can say standard at exit. Okay, so it is lowercase. It seems like that's how it is in hold on, we'll say exit stuff. Exit stuff. Oh, we haven't included it yet. We're gonna include this before print shit. Need at functions for at exit. So we do the user defined stuff first. Because we know that the non-user defined stuff has header guards and is good to go. And if print shit is dependent upon something, then I can make sure to already include that in print shit and fix it first. So it's basically fixing the user stuff first, because we know that the non-user defined stuff is probably fine. So at exit, we're going to do exit stuff and print shit, and we don't want to call it here. Don't do print shit because we aren't calling. We pass standard add exit takes a function pointer. So standard exit can call that function by referring to its pointer, I think. And now we can say standard exit and then boom, like this. But then we have an error. What is the error? Exit. Oh yeah, we need the code. Standard exit needs a what do we call it? Just like an exit code, I think is what it's called. So we'll just say 0 because that's correct. Cool. Okie doke. We have unreachable code. Is it because of the return? It seemed like it was. Yep. And so we could say bool or const expression bool cleanup needed, or we could just say cleanup needed. These are separate words. And true, cleanup is needed. And now we can say if cleanup needed, then it'll do this. That way we can say in not all cases, sometimes we want to return 0, but other times we want to return 1. Well, in this case it should also be 0, but maybe we want to indicate something for cleanup is needed, so we can say 0, or we can say cleanup. So it'll say exited with code 1 because it has cleaned up. Process 2116. Let's see what happens if we don't do that and it's just whatever's default process. Oh, 12724. Is it always the same? No, it's different. Was it the same if I do this again? Oops. That was because we weren't giving it the code. Oh, okay. All right. It's a different process every time, seems like. Bop, bop, and bop, bop, and bop. Okay, cool. We're saved. Okie dokie. So we have halt, we have abnormal termination, standard abort. Okay, so you could say, like, if something is func and we're not able to handle the error, or just something happens, like if, like, we could have stuff built into the system, like if the memory capacity is just too high and we don't have a way of cleaning it up, then just fail the thing, just like a reactor. Maybe we have cleanup stuff as long as the reactor is under 85%, but we know that if we exceed 85%, or let's say 80%, so when it exceeds 80, then it does the cleanup stuff. But if it exceeds 90, we know that that's the point of no return. We don't have stuff that is sophisticated enough or good enough to clean up and get us back below 90% usage. So if we're at 90%, just abort, just kill the program to avoid whatever, messing up the software or the program or the hardware or something like that, the system implementation. We can do standard abort. Okay. And I think standard abort probably needs that code too. We can test it. Okay, and we can just do standard abort. Okay. Oh, it does not take an argument. It actually just takes, it's just whatever it is. And we can say, concentration bool, should abort, and then we'll say true, and then if should abort, and then boom, like that. So it's not happening in every case. Okay, what happened? I accidentally typed something. Oh, good God. Oh, here it is. So debug error. Abort has been called. Interesting. Ignore. And it is code 3. Okie dokie. That's cool. I don't think I've ever called that. Alrighty, so it's abort. Algorithms. Yep, so we've got some sort of algorithm is like a sequence of, well, I guess it doesn't have to be a sequence, but a sequence could be a sequence of one. So a sequence of expressions or operations to return some sort of value. Yep, so sequence of instructions in this case doesn't necessarily have to be expressions, seems like, but maybe it probably does. It is stateful if it retains some information, meaning stateful, meaning it has some sort of state, and then we call it and it adjusts that state, and when we call it again, it is operating on the same value that it left off with. It is stateful. Versus stateless would be an algorithm for calculating, let's see, so we could have an algorithm for calculating the force of something. So I toss an object off a building, and it starts falling because of gravity, and the mass at the center, or in the mass, I guess, of the Earth is more concentrated at this particular point, which pulls other things in due to just the force of gravity, at least as we know. So the object starts going down, and we have a function to describe it, and we could just say force is mass times acceleration. So we say mass of the object is 5 kilos, acceleration 9.82 meters per second squared, and then boom. Oh, okay, so we say it's about 50 newtons or something like that, going downwards, or going down in like some sort of arc-ish, something like that. Assuming that there's no other acceleration. We've already dropped it, so maybe there's some extra force, so maybe it's 11 meters a second squared because we've added some sort of initial velocity to it, something like that. So then we simply pass in those parameters. We pass in any initial acceleration, and we pass in the mass of the object, and then this algorithm yields the force. But we don't save that because we calculate it for each object. So the force of this one, the forces acting on this one object are totally exclusive and do not affect the forces on this other object. So when we calculate it again later on, what is the force of this guy as acting on this guy's face as I hit him with a right hook and then slip his left hook? Well, we pass in the mass of whatever's hitting him. Maybe it's just more than the fist because it's part of the body, so there's some sort of added mass. Maybe it's like 30 pounds instead of 5 pounds or something, or 4, whatever a fist is, probably 2 pounds maybe. Boom. And then the acceleration, so it's whatever from here to here. there's some sort of and there's some sort of acceleration. We pass it in, and boom, and it would have nothing to do with the state that was previously saved for calculating the object falling. That force has nothing to do with the next one. That is a stateless algorithm. Cool. Okie doker. So we have that as state. The current value is held in stateful variables. So like a Mersenne twister, for example, is stateful and it has a big ass state. It's got like what was it? It was like 16 or 600 bytes or some shit of information that it stores, just some ungodly amount. And it's like whatever it is, 133 or 19937 or something, some huge amount of a state, like 2 to the that, which is just ungodly, some huge amount, some huge number. Cool. So stateful, and then deterministic if we have it and it is known. It seems like algorithms are probably by definition deterministic because it produces the same output for a given input. But you might say like maybe not, because let's say in this algorithm there's an algorithm, but each time the algorithm gets a random result, or it goes to random device and calls random device's operator parentheses, which outputs some random integer, and then boom, that algorithm adds a random integer every time. So you call it, it is not the same result every time. It is not known. It will not always produce the same output for the same input. And we could make that right now. So we could say a yeah, sure. So we'd say non-stateful algorithm. If not defined, non-stateful algorithm H. Define non-stateful algorithm H. And if, to end this conditional preprocessor directive, namespace algorithm shit, and we'll just say, let's just say it's a void. All right, well, we'll say it's an int. We're gonna return an int. That's fine. Return an int. Return an int. Get random result. Cool. And then, oops. And then it takes an int. We'll just say operand. Sure. Oops. And this needs to be a for declaration. Oops. And then we'll do non-stateful algorithm, include non-stateful algorithm, namespace. Excuse me. Oops, turns out you can copy nothing. Never mind. Okay, well, maybe. I don't know. Something happened. Cool. And so what we'll say here in get random result is it will return an int. This header file is going to need include random. Want random standard random device for random nums. It's not a huge, I don't think it has a huge, what is it called, like not matrix, like not the repeat pattern, but like how many different numbers it can possibly give. So we could say return, yeah, we can create a random device here. So we could say return operand plus standard random device, and we initialize them and call them right there, and then boom, like this. Oops, and there's an issue here because we've at least not done that, and then now there's an issue because 7 returning operand plus random device is called, oh, I think we're missing a parenthesis. Okay, cool, that's why. Noted. And and the problem here is that this gives an unsigned int. So first we're gonna do, okay, so we're gonna do our millionth parentheses here, and we're gonna say static cast to an int, and boom. Cool. Holy shit. Is this really how the parentheses are gonna go? Well, I guess we could just say operand plus that. We don't need all these. So we could say random device, that's the call. And then this is right here. Or sorry. This is the well, I guess it's the operand. No, it's not the operand, but it's an expression. It's the call to operator parentheses for this unnamed random device that we have value initialized. That return result or that return value is converted to an int via static cast to an int, and then take the whole thing instead of plus static cast and then something like here. There's some sort of funky operand stuff here, and then we'll just say include non-stateful algorithm, and then we'll just say algorithm shit, and then get random result. Boom. And then in this case, it just returns that. So we'll say we also need stream need to output random result. Need random result getter. Cool. And then here we're gonna just say we're gonna output it. Cute, like this. Bop. Okie doke. So in this case, I forgot to call it. So we're, I guess, giving. Oh yeah, we also want to say initial value. So we'll just say constant expression initial value. Oops. This also needs a data type, which will be an int in this case. We'll just say it is 6. And so we'll just say initial value. Oops. All right. Cool. And now we're cool. The issue here is we were passing the identifier itself, get random result, which is a pointer to it. It seems like if I just pass the identifier, by default, it seems like I'm passing somehow where the identifier is located in memory, I guess, something like that, because it's using an address. So 17, -2. Hey, yo, we're passing the same initial value, bro. Why is it giving me different results? Well, it's because it is one non-stateful. Oh shit! Oh, I deleted the fucking main file. God damn it! All right, well. Fine. Why is it a header file? It's because it is not deterministic. The state part doesn't matter. Cool. Let me check my phone really quick because my buddy's getting on to play games in a while and just hang. Let me check. Like, tired. Hey, check so. Okay. I'll text because this boy doesn't respond. Okay, yeah, we have pseudo-random number generators, which are deterministic. Well, I guess they're not necessarily deterministic. They approximate randomness, so they give seemingly random sequences of numbers. And we can get a specific number from them if we want. We could output a whole bunch of shit. So we can call it and get a random number. We can seed it. We can use a seed sequence, which is a variable that takes, it seems like multiple integers, or at least multiple numbers, and then stores them as one object, and then we pass that into a Merson twister in order to seed it full of all the different variables. I think it takes like 8 or something like this. Okay, there's underseeding when it hasn't been given enough info, so like, oops, here we go, let's see. Alright, so playing like an hour. If I have a Merson twister and or some pseudo-random number generator, and let's say that I only seed it with some small numbers, well maybe, let's just say it adds some random number from like 1 to 10,000. Well, if I gave it a huge seed, then it would be adding that to a giant number. But if I instead gave it a small number, and its state had a whole bunch of zeros in the beginning, because it's used to expecting this big number, instead I only give it a small number, 0, 0, 0, 0, 0, 0, 0, 5, 7, 6, 4, 2, 3, 4, 8, whatever. Well, it's going to take a while for it to start giving the quality answers that it's going to give later. Because if we let it warm up by running it a whole bunch of times, eventually it'll keep adding and adding and adding, and then it'll be 6, 7, 8, 2, 1, 6, 7, 8, 4, 8, 2, 3, 4, 7, 7, 7, 7, 7, 1, 8, 2, 8, 3, big numbers, and then the next number will be the same size, keep going, boom, 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 boom. But instead, if we don't do that, and we don't warm it up after we underseed it, then it'll be small number, small number, small number, bigger, 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 bigger. Finally, numbers that are as big as we're looking for. Okay. Yep, the initial value is the random seed. Well, I mean, it's not random yet, unless we're actually giving it a random seed, because we might just be giving it the same one. If we asked for user input, well, it's a seed, sure. We're initializing it with some initial state. We haven't made it random yet, so but it should be getting a random seed. So we could use a seed sequence and pass it steady clock. So we could pass it a whole bunch of shit. So we could pass a seed sequence, a bunch of calls to the random device, because apparently that's the easiest way compared to steady clock. And then we could also pass it a steady clock, so it depends upon random numbers and the current time. So even if you can predict the random numbers, well, maybe it's harder because now there's time involved. So, because the numbers are off by some amount, and then, turns out it's time. And then you have to run the same shit with the predictions over a 24-hour period to figure out when it finally matches again or something like that. So, should make it harder to crack so that your drops seem more random and aren't, oh shit, when I do this in this way, I'm more likely to get this drop from the boss. I mean, maybe it makes sense because you're like, in Dragon Quest, you use some sort of thief skill in order to remove an item from an enemy, and then you know that if the item, maybe the enemy has a certain amount of drop chance, and by default it drops that first item. But if you take the first item, then that drop chance is an actual item that gets generated instead of the default item that it's holding, which that's always a fucking Jasper berry or some shit if it's Pokemon. Well, now it's more predictable. But if we instead remove that and we add in some uncertainty, then it's less predictable. Something like that. So we could add steady clock. So we could say get standard chrono, just time shit, I guess. Chronographic time. I don't know. Chrono. What's the thing you shoot guns with? A chrono? Chronometer? Cronus? Isn't it the cheating controller thing? A chrono? You got a Cronus. A chronometer? Chronograph? Chronometer? I don't know. Something when you shoot, like, especially airsoft guns, too, to get the feet per second and know the speed. So, we could add in standard chrono, steady clock, and then cast the return value of steady clock into the return type, or to be the return type of immerse and twister. That way we can fucking pass it. So it's probably converting it to an unsigned int. Then, in parentheses, we can get the now from the steady clock, and then we can get the time since the last epoch, whatever the fuck that means. I guess the last time that it was called, I guess. Time since last call or something like that. So we could do like time, and then call it again, and then it's taking time, and then call it again, and then it's taking time. Or maybe an epoch is like every hour it happens or something. I don't know. I don't even know. Or times, maybe the epoch is the time that steady clock has been seeded. It was given us, and it's 55 years ago, and 2 hours and 3 days, and fucking 3 days and 2 hours, whatever the hell, right? We pass that, and we pass the now, time since last epoch, count the seconds per whatever. And then we pass that into the seed sequence, and then a bunch of other random stuff. That way we seed it with all the info it could possibly need to make warming up easier, and then boom, we get more quality numbers. Qualitier? Jesus. So when it's initialized with a seed, it's been seeded. The size can be smaller than the size of the state. When that happens, it's been underseeded. It's not complex enough for what it wants to generate stuff properly. So if we want to generate 10-bit numbers, but I only pass it a 2-bit state, fucking like from 0 to 4, well, or 0, 1, three. Oh, okay, so I guess 0 to 3, because each one has 2 answers. So 0, 1, 2, 3. Seeded. Cool. Oh yeah, because if we pass a 10-bit state one, a 2-bit, hasn't been seeded all the way. We got to pass it a whole number and then operate on that whole number to give the big quality numbers instead of having it add stuff and then give low quality numbers, a bunch of zeros. The length before it repeats itself, okay, it's the period. So each one of them has a period. It's just, I guess, statistics, just the odds of it eventually repeating itself and getting itself stuck in some sort of pattern. This seems inevitable. But try and make it as long as you can. Yep. Output into some other distribution. So it's like, oh, okay, you gave me this. I'll convert them to this. It's a random number. And a uniform distribution is a random number that has outputs with equal probability. So instead of it being random amongst random number, it should be uniform, but it doesn't have to be. It could be. It's between 1 and 20, sure, but maybe it's 20 95% of the time. Maybe it's 20 all the time. I guess that wouldn't be random then, but okay. The quizzes are getting harder. Oh boy. Okay. How long? All right, I'll do brain break and then we'll go in a bit because I'm just tired today.